Chapter 3 Non-Aqueous Solvents. Most of the chemical reactions are carried out in solutions, and the behavior of substances also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification together with its favorable physical and chemical properties such as long liquid range, high dielectric constant, specific heat, heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water, which are used for carrying out chemical reactions, are called non-aqueous solvents. Attempts have been made to find some other substances which could behave as good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid ammonia, H2SO4, liquid HF, liquid sulfur dioxide, etc. which have been frequently used. In the present unit, we shall discuss briefly the important features of non-aqueous solvents such as NH3 and SO2. Physical properties of solvents and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reactions and separate the products more conveniently. Some of the important physical properties of the solvents are discussed below. First one, melting point and boiling point, liquid range. The melting and boiling points of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reactions in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling points for some common solvents are given. In table 1, melting points and boiling points of some common solvents. Water 0.0 melting point, 100 boiling point. NH3 minus 77.7 and minus 3.4. HF minus 89.3, 19.5. SO2 minus 75.5, minus 10.2. CH3COOH 16.6, 118.1. H2SO4 10.4, 300 boiling points. It is clear from the above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperatures, while NH3 and SO2 can act as solvents only at low temperatures. Second, physical properties: heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization helps to know the nature and strength of forces which hold the molecules of the solvent together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of the substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitudes of molar heat of fusion and molar heat of vaporization gives us insight into the nature and strength of the intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called the Troughton's constant. For normal liquids, if molar heats of vaporizations are expressed in calories and boiling point in absolute scale 0 Kelvin, then the Troughton's constant has the value 21.5. If heat of vaporization are in joules, Troughton constant is about 90 for normal liquids. Such liquids exist as independent molecules without any bonds between them. A higher value of Troughton's constant indicates associated molecules. For example, common solvents like water, ammonia, hydrogen fluoride have Troughton's constant value greater than 21.5 and are therefore associated liquids. The molecules of these liquids are polar. The association of polar molecules is due to their tendency of orient themselves so that the oppositely charged ends of the molecules come near to each other. The molar heats of fusion and vaporization of some solvents are given. Water 6.0 molar heat of fusion, 40.65 molar heat of vaporization. Ammonia 5.65 and 23.56. Sulfur dioxide 7.40 and 24.94. Hydrogen fluoride 4.58 and 30.26. The inspection of table 2 show that the values of molar heats of fusion for water and ammonia are almost same. This means that the forces which hold molecules together in water and ammonia are of same magnitude. Third physical property, dielectric constant. This property is a measure of the polar nature of the solvent and helps to estimate the solubility of polar or non-polar substances in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q positive Q negative by epsilon naught R square, where Q positive and Q negative are the charges of the cation and anion respectively. R is the distance between them equal to the radii of the ions. Epsilon is a constant called dielectric constant of the solvent. If epsilon is large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions and hence it will be easy to dissolve an ionic substance. Thus, in solvents of high dielectric constants, the ionic substances will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. The dielectric constants for some common solvents are H2O 81.7 at 18 degrees Celsius, ammonia 22 at minus 33.5 degrees Celsius, SO2 17.3 at minus 16 degrees Celsius, CH3COOH 9.7 at 18 degrees Celsius, HF 83.6 at 0 degrees Celsius, HCN 123 at 16 degrees Celsius, DMF 36.7 at 25 degrees Celsius, H2SO4 100 at 25 degrees Celsius. It is clear that solvents like HF and H2O are good solvents for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvents like ammonia and SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compounds, and especially those containing multi-charged ions. For example, carbonates, sulfates and phosphates are practically insoluble in liquid ammonia or liquid sulfur dioxide. Fourth property, dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moments have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity results in strong bonds between the solvent and the solute molecules and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and helps in dissolving the solute. The fifth property, viscosity. It is a measure of fluidity of the solvent. Solvents like water, ethyl alcohol and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rates at ordinary conditions. In solvent of low viscosity, the operations which such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increasing the viscosity of liquid, increases the difficulty of such operations. Types of solvents. Non-aqueous solvents have been classified in many ways. The following are the important classification based upon the chemical properties of the solvent. First, protonic and non-protonic solvents. Second, acidic, basic or amphiprotic solvents. Third, ionizing and non-ionizing solvents. Fourth, coordinating and non-coordinating solvents. Then the first one, protonic and non-protonic solvents. The solvents from which protons can be derived are called protonic or protic solvents. Therefore, protonic solvents contain ionizable hydrogen. Common examples are H2O and HF and H2SO4 and HCN. The solvents from which protons cannot be ordinarily derived are called non-protonic solvents. These are also called aprotic solvents. In other words, these solvents do not contain ionizable hydrogen atom. Common examples are liquid SO2, N2O4, C6H6, CHCl3 and CCl4. Second, acidic, basic or amphiprotic solvents. The classification is based upon the acidic or basic behavior of solvents. The solvents which have a strong tendency to donate protons are acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride, acetic acid, etc. Solvents which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvents. For example, liquid ammonia, pyridine, hydrazine, ethylene diamine, etc. The solvents which neither have a strong tendency to gain nor a strong tendency to lose protons are called amphiprotic or amphoteric solvents. In other words, they neither behave as strong acidic nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Third, ionizing and non-ionizing solvents. The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some common examples are H2O, NH3, HF, SO2, N2O4, ClF3, BrF3, POCl3, etc. These ionize as H2O plus H2O goes to H3O positive plus OH negative. NH3 plus NH3 goes to NH4 positive plus NH2 negative. HF plus HF goes to H2F positive plus F negative. N2O4 goes to NO positive plus NO3 negative. 2ClF3 goes to ClF2 plus ClF4 negative. 2POCl3 goes to POCl2 positive plus POCl4 negative. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbons. These are non-polar or non-ionic in nature. Fourth, coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, NH3, SO2, dimethyl sulfoxide, acetonitrile, dimethyl formamide, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvents. For example, CCl4, saturated hydrocarbons, etc. These are not of much interest to inorganic chemists. Types of reactions in non-aqueous solvents. The following types of reactions commonly occur in non-aqueous solvents. First, metathetical or precipitation reactions. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reactions. These types of reactions can be predicted if the value of the solubility products of the compound formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. On the other hand, in liquid ammonia, a precipitate of silver chloride combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Therefore, reversal of chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. Second, salt formation. The reactions between appropriate acidic and basic substances to form salts are called salt formation reactions. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, sodium salt of urea is unstable in water and uride ion will take a proton from water to form hydroxide ion. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. Third, acid-base reactions. The acid-base reactions in non-aqueous solvents can be explained on the basis of solvent system concept. As already learnt, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristic of the solvent. Similarly, a base is a substance that gives the anion characteristic of the solvent. The acid-base behavior of substance depends upon the acid-base nature of the solvent, the character of the solute, and the solute-solvent interactions. In the case of protonic solvents, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ion act as acid and NH2 negative ion act as bases. The neutralization reaction is NH4Cl plus NaNH2 in the presence of liquid ammonia gives NaCl plus 2NH3. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis acid base type of reactions can occur because of non-ionization of the solvents. The acid-base behavior of a solute in a solvent depends upon the acidity or basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. Fourth, solvolutic reactions or solvolysis. The reactions in which the solvent molecules react with the solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute molecules or ion, are called solvolutic reactions. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anion is changed. For example, the solvolutic reaction in water, ammonia and ethanol are given in some reactions. First, water as solvent. 2H2O goes to H3O positive plus OH negative. This is autoionization. SO2Cl2 plus 4H2O goes to SO2 OH whole twice plus 2H3O positive plus 2Cl negative. Here, concentration of H3O positive is increased. F negative plus H2O goes to HF plus OH negative. Here, concentration of OH negative is increased. Ammonia as solvent. 2NH3 goes to NH4 positive plus NH2 negative. SO2Cl2 plus 4NH3 goes to SO2 NH2 whole twice plus 2NH4 positive plus 2Cl negative. Concentration of NH4 positive is increased. H negative plus NH3 goes to NH2 negative plus H2. Here, concentration of NH2 negative is increased. Alcohol as solvent. 2C2H5OH goes to C2H5OH2 positive plus OC2H5 negative. SO2Cl2 plus C2H5OH goes to SO2 OC2H5 whole twice plus 2C2H5OH2 positive plus 2Cl negative. Here, concentration of C2H5OH2 positive is increased. CH3 plus C2H5OH goes to OC2H5 negative plus CH4. Here, concentration of OC2H5 negative is increased. It may be noted that in case of solvents like water, ammonia, alcohol, acetic acid, etc., the terms hydrolysis Ammonolysis, alcoholysis, and acetylysis are used respectively. Fifth, solvation. The reactions in which the molecules of the solvent get attached to a solute species, cation, anion, or molecule are called solvation reactions. The species formed is which is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammonolysis, ammoniation, alcoholation, etc. And the resulting solvates are called hydrates, ammoniates, alcoholates, etc. For example, CuSO4 plus 4NH3 goes to CuSO4 dot 4NH3. This is ammoniate. CuCl2 plus 4H2O goes to CuH2O whole 4 2 positive, 2Cl negative. This is hydrate. BaSO4 plus 3H2SO4 goes to BaSO4 dot 3H2SO4, solvate of sulfuric acid. Solvation of a cation occurs through ion dipole interactions between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donate a pair of electrons to the cation. On the other hand, solvation of anion occurs through ion dipole interactions between the negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia, or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis, because in many solvolytic reactions the first step consists of solvation reactions. However, the term solvation is used for those reactions in which the solvent molecule remain in the resulting product. Let us discuss some reactions in two common non-aqueous solvents. Liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvents. It is now a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble those of water. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following points. First, liquid range. The melting and boiling points of liquid ammonia are lower than those of water. In liquid ammonia, the liquid range is from -77 to -33 degrees Celsius, and therefore it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Second, hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element, nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NH bond is weaker than OH bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated than water, it is a better solvent for organic compounds. Third, dielectric constant. The dielectric constant of ammonia is lower as compared to water, suggesting its lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic compounds. Soluble salts include most ammonium salts, nitrates, thiocyanates, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia has lower viscosity than water, and this might be expected to promote greater ionic mobilities and therefore compensate to some extent for the effect of dielectric constant. Fourth, self-ionization. Both ammonia and water show comparable self-ionization as represented. 2NH3 goes to NH4 positive plus NH2 negative, and 2H2O goes to H3O positive and OH negative. However, the extent of autoionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. K of NH3 is equal to NH4 positive, NH2 negative is equal to 1.9 into 10 की power -23 at minus 50 degrees Celsius. K of H2O is equal to H3O positive OH negative is equal to 1 into 10 raised to power minus 14 at 25 degrees Celsius. Therefore, ammonia can conduct electricity to a feeble constant extent. Ammonia as a better solvent than water. The following properties of ammonia make it a better solvent than water. First, liquid ammonia is a very poor conductor of electricity. Second, the specific heat of ammonia is more than that of water. Third, liquid ammonia is less viscous than water. Most salts, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia, which is about 1 by 3 of water, but due to low viscosity, which greatly increases the mobility of the ions. Fourth, liquid ammonia has high critical temperature and pressure. Fifth, it is less associated than water due to lesser hydrogen bonding and therefore is a better solvent for organic compounds. Sixth, liquid ammonia forms strong reducing metal ammonia solutions with alkali metals, therefore it is an excellent solvent for many reduction reactions. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvents and has been widely used in industry. Under normal conditions of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and is easily maintained in the liquid phase. It has a wide liquid range, minus 10 degrees Celsius to minus 75.5 degrees Celsius, and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove traces of water. Its dielectric constant is small and therefore is a good solvent for covalent compounds. The characteristic and physical properties of liquid sulfur dioxide are: freezing point minus 75.46, boiling point minus 10.02, density 1.46 at minus 10 degrees Celsius, viscosity 0.428 at minus 10 degrees Celsius, dielectric constant 17.4 at minus 10 degrees Celsius and 15.6 at 0 degrees Celsius, dipole moment 1.61, specific conductance 4 into 10 raised to power minus 8 at minus 10 degrees Celsius. Structure of sulfur dioxide molecule. Electron diffraction studies have shown that sulfur dioxide in gaseous phase has the angular structure, and the valence bond theory predicts that the SO2 molecule is a resonance hybrid of the following two resonating structures. Solubility of compounds in liquid sulfur dioxide. Among the inorganic compounds, iodides and thiocyanates are most soluble. In case of alkali metal halides, the solubilities are in the order Mi is greater than Mbr, is greater than Mcl, is greater than Mf. The uninegative polyatomic anions such as ClO4 negative, NO3 negative, BF4 negative, etc. are generally more soluble in liquid SO2. Salts of multi-negative anions such as SO4 negative, SO3 negative, S2 negative, O2 negative, etc. are practically insoluble. Many of the ammonium, thallium and mercuric salts are soluble. It is an excellent solvent for covalent compounds. Many covalent substances like halogens, interhalogens, phosphoric halides, oxyhalides of sulfur, phosphorus and halides are soluble in it. Metals are insoluble in liquid SO2. Among the organic compounds, aromatic hydrocarbons and alkenes have very high solubility in liquid SO2. In comparison to saturated hydrocarbons, alkanes, pyridine, quinoline, ethers, halogen derivatives and acid chlorides also dissolve in liquid SO2. Many compounds dissolve in liquid SO2 due to the solvate formation, for example, Ki.4SO2, CaI2.4SO2, KSCN.SO2. Many donor molecules also form stable solvents with SO2. For example, C5H5N.SO2, C6H5OCH3.SO2, BF3.SO2, etc. Autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to ionize as 2SO2 goes to SO2 positive plus SO3 to negative. The thionyl ion SO2 positive is analogous to the hydronium ion, that is H3O positive, and ammonium ion NH4 positive, and sulfite ion SO32 negative corresponds to the hydroxyl OH negative and amide NH2 negative ions of the aqueous and ammonia system respectively. Some special features of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantages over other solvents as a reaction medium. Some of these are: first, it has low boiling point and this allows its easy evaporation and therefore removal from the reaction mixture. Second, it has low melting point and therefore it allows reaction to be carried out at low temperature. Third, liquid SO2 is an inert solvent. Fourth, it has unusual solvating powers for both covalent and electrovalent compounds. Fifth, it is a better medium for covalent compounds like hydrocarbons and is used for the purification of some petroleum products. Fifth, it is used as a diluent for the superacid medium, which helps in reducing its viscosity without affecting its acidity.